All right, well, why don't we get started? Welcome to another Two Green Energy webinar in which we tackle the tough issues associated with the migration to renewables, and in particular, the business ramifications. A great number of the subscribers to the newsletter at Two Green Energy and the participants in the blog and so forth are there simply because they're interested, they're advocates, and they all believe that this is a good idea, or at least most of them. But a great number of people want to be participants in this multi-trillion-dollar industry as it unfurls over the coming years and decades, and they're looking for information and services associated with that. So what I try to do is hunt up guests who can speak not only to the technology but to the business implications of it. And I could have looked a heck of a long time and not found anybody more qualified to do this, to participate at that level than our guest today, Dr. David Doty. David, welcome.
Well, thanks for inviting me. Happy to be here. Happy to speak to some of the issues that I've been looking into very closely for a long time. I think I have some insights from the perspective of a physicist, chemical engineer that are unique, and have enjoyed your website, the book that you mentioned there that was a bestseller, great book, and hope that I can contribute.
Well, I know you can, and thanks so much for being a part of this thing. We met, I should mention, I do this thing called Craig Shields at Your Service, which is a little kind of funny moniker that a friend of mine suggested, in which I spend a day with various types of people for various reasons, and I really have no issues with respect to those reasons. They can be extremely broad and varied. And you hired me to come meet with you and your lovely wife and talk about the whole issue of wind fuels, and we'll get into this and how to best take this technology to market, considering that marketing, that was, back in the day, that was the way I made my living. I was a marketing consultant to technology companies for 30 years. It was a fascinating day we spent, and I hope that in this hour that we're going to spend together today, that we can kind of revisit some of those issues that we talked about that day and kind of make this presentation about wind fuels and about the kind of promise that it represents. I also want to mention that if the audience has questions, please just write them into the sidebar on the left, and we'll field as many of them as we can. Let me just go back. I think we're fine here. All right, so I want to talk, the beauty of your presentation, it seems to me, is that it's not just a rah-rah, it's just not a fan club for a specific energy solution, but it's presented in the context of world energy, and that's why I've called this webinar The World Energy Picture by 2050. In particular, you talk about the context in which there are imperatives to move away from our traditional energy solutions, and some of the likely suspects, some of the things that, for instance, my pet technologies, your position is they're not really going to scale as well as some people think. Why don't we talk a little bit about just the basic energy context and circumstance here, and just take us through what you believe.
Yeah. Well, I'm quite convinced that we're going to very shortly see the end of the growth of conventional oil. It'll continue to produce for several decades at declining rates because conventional reserves are being depleted. Discoveries have not matched use for 15 years or more. There's plenty of unconventional reserves to be tapped, tar sands especially in Canada and Venezuela, but it takes a lot of investment and time. Of course, there are huge environmental issues associated with producing oil from those. So the price of oil unquestionably is going to continue to rise, as we've seen, of course, for the last several years after it crashed, mainly because of the world economic crisis. But this increase in the price of oil, I think, will continue steadily, of course, with ups and downs. And as demand increases, especially from developing world and third world countries, but alternatives also are limited. Yes, there's a lot of coal, but if it supplies more of our energy, then it'll be depleted faster. That is, it could be converted to liquid fuels, but that'll reduce the time that we have sufficient coal. And even uranium faces limits with our current method of using it, which is quite inefficient in the once-through plants. Natural gas, yes, there have been more discoveries, and they've learned how to produce the shale gas at lower cost and more efficiently than what was appreciated several years ago. But still, the natural gas reserves are limited, and much of that shale gas will be more difficult to produce than what has initially been produced, and often it contains a lot of CO2, which has generally been ignored. So there are issues with all of these resources. They're limited, and the demand is steadily increasing, and we would like to see the developing economies improve. They're going to need energy. So we see a crunch coming soon in oil, and not too long after in our other energy resources, unless we develop economic alternatives.
Yes. Well, before we leave this thing about oil is particularly important because of its portability and use in transportation, where these other things have to do to a large degree with the electricity on the grid. But I saw a presentation on oil the other day that talked about peak oil in particular, and this guy may have been oversimplifying, but he said, look, if you want proof of peak oil, all you have to do is follow the money. All you have to do is notice that when oil went from $40 to $140 a barrel, there was very, very slow increase in production. So in other words, if there were ever incentive to pump that stuff out of the ground, it certainly existed, and it resulted in fairly small increases in production. Is that correct?
Indeed. It takes a long time to increase production from these conventional resources. Large amount of investment. These large projects never move quickly. So yes, with increasing price, there can be some increase in production, but it will take time, and there will be severe limits before there are no more conventional resources to be produced at increasing rates.
Yes, and Matt Simmons, the late great Matt Simmons of peak oil fame, said, when I interviewed him on the subject, he goes, well, the problem with unconventionals, Craig, is that they're unconventional. In other words, it's not true that we're out of oil. It's not true even necessarily that we're running out of oil, but we're certainly running out of inexpensive, easy-to-find oil.
Indeed. And,
all right, well, why don't we go... Oh, go ahead, sorry.
We'll get to at some point.
Sorry?
Yes, we have been worrying about that for quite some time and have been working on an alternative, as we'll discuss a little later on.
Yes, very good. But before we get there, let's just go through some of these other issues in terms of forming the imperative for the kind of solution that you're aiming for. So you want to talk a little bit about biofuels?
Yes, I think the resource there is much more limited than has been appreciated. Easiest way to see that is to just assume, for example, if we were to put all of our biomass resources into co-firing in place of coal, we would only be able to replace somewhere in the neighborhood of 7 to 9% of our coal usage, probably with wood. So clearly, the biomass resource is very limited. The biofuels resource is even more limited because of losses associated when you convert biomass to liquid fuels. And the net energy is yet less because it takes a lot of fossil fuel resource to produce the biofuels and fertilizers and cultivation, processing. So maybe the gross contribution of biofuels last year was in the 3 or 4% range, but the net contribution was probably about a quarter or a third of that. And we've seen what it's done to the price of food and grain. Of course, not steadily, but many years have seen such strong increases now over the last 5 years. Again, of course, over the last year. And when you till new soil, carbon is brought up, biomass plowed up, exposed to air, oxidizes more quickly. There's a carbon debt associated with that takes a long time to be repaid. So we need to be very careful about allocating more land to biofuels. It's needed for food. And,
right.
And of course, fertilizer runoff is really affecting the oceans. Gulf of Mexico is one of the most famous areas, but other areas around the world as well.
Yes. Well, okay, so let's go to this slide on other kinds of biomass, and talk, if you would. I'm not sure whether we have a slide on algae, but if we don't, please speak to this, because the guy I interviewed in my book on the subject said was all about algae, and in particular that little is good, and he went through this analysis of how you can get you extract energy 30 to 50 times more efficiently through algae than you do any terrestrial plant, and he thought this was, a good thing.
Well, that's an exaggeration. I think there is a slide a little later on algae, so maybe we can defer more of that to when that slide comes up. And there's been a lot of hype about cellulosic ethanol for the last decade, and it simply hasn't proven to be cost effective. One of the big reasons is cost of feedstocks that were $25 a ton when much of the talk began and incentive began on cellulosic ethanol. Or now they're typically around $100 a ton for the low grade feedstocks and higher for the high grade feedstocks, and steadily going up, as we see in the price of wood pellets, for example. And if the feedstocks are $300 a ton, the ethanol from that will be at least $4.50 a gallon. And need to keep in mind that ethanol has only about 2/3 of the energy content of gasoline. So, as a comparison to gasoline equivalent, it's somewhere in the neighborhood of $6.50 a gallon gasoline equivalent. So, I just don't think that that has a lot of promise, nor algae, and there's for economic reasons, and that there's been a lot invested in algae for some time, and all the demonstrations have proven that these processes involving solid liquid separations, taking the lipids out of cells, are expensive. They can't be scaled up well. The dry algae itself is expensive. Currently, the low end of the cost is around $5,000 a ton, but someone has commented that the actual cost is maybe 3 orders of magnitude higher if you look at the global average, looking at all the investment in algae over the last couple of years and the amount actually produced. But it can be produced certainly in the range of several $1,000s per ton, I'm sure. But there are a lot of steps required that don't readily scale up. So prices, for example, from green fuels, they spent $70 million and produced almost no fuel. And BPR, I think it was, or another company, forget now, spent $20 million, and the cost of the fuel they produced was in the neighborhood of $40,000 a gallon. Well, yes, it was pilot, it was research, but I think that gives you a pretty good clue. Well, one company that was trying to develop algae oil has abandoned the green algae, gone to sugar-fed algae, because it is easier to get fuels as long as the sugar is cheap, but it's still is complicated, and they've sold some of their fuels at over $400 a gallon. So that gives you some clue as to costs even with that approach.
Well, the real issue here, it seems to me, is not do these things hold promise in the laboratory, but do they work when at scale? And your position here is that they don't, and I guess that's supported by the evidence so far, but I'm sure that the people still working on these things would argue that.
Well, indeed. Of course, the latest, maybe fairly comprehensive study that came out of a DOE-supported lab, Berkeley, projects that oil fuels from green algae will be able to be produced for $10 a gallon. I disagree. I think there are some unrealistic assumptions in their projections. I suppose that could be possible after several $1 billion worth of investment in any one area. But the algae ponds, it's all largely going to be, they're going to be produced from local labor, and there's got to be local training. It's not the kind of thing that you can really do in a factory, or at least a large portion of the technology won't be done that way. And so I think there are these hurdles to scale up that one doesn't have with chemical processes of the type we're talking about, similar to those that have been used in gas to liquids.
Yes. Well, okay, I'm with you on that. But before we get into that, and by the way, we are heading into this kind of synthetic fuel discussion, which, by the way, itself hasn't exactly set the world on fire in terms of, demonstrable success. So you have some explaining to do there, Doc. But yeah. Before we get there, let's talk about some of these others, because I do think that the understanding the whole context of renewable energy, and not only on the grid, but also in powering electric vehicles, or at least alternative fuel vehicles, is an important one. You want to take us through some of your viewpoints on this?
Well, I think electric vehicles will have an increasingly important role to play, but it will be very limited. We've seen just in the first quarter of this year, first quarter of real introduction into this market, how slowly they're being accepted. I think maybe 400 or 500 were sold in the first quarter. That doesn't make much of a dent in demand for conventional fuels. Even if they were selling 1 million a year, it would take a long time, but we're a long way from that. So I think they'll scale up slowly because people in large countries such as U.S., Canada, Australia want more range and more luggage space. So we think we need to continue to worry about liquid fuels. CSP, concentrated solar power, has been perceived by many, some very bright people, to have enormous potential, but it's been fairly mature for 3 decades with very little decrease in price, really very, very stable, surprisingly stable in price. And if you look at actually in the last couple of years, there have been some projects where it may have been below $3.50 a watt with no storage, but there are some examples where it was approaching $8 a watt with 6 hours of storage. Molten salt's not new. It's been around for storage for 3 decades. So it's not going to change the picture. I don't see any way to really bring the price down for that to have a large impact or contribute a large fraction of our energy needs.
Okay. There certainly are people who disagree with you on this, insofar as as a matter of fact, the guy, not to keep going back to this book, but the guy I interviewed on CSP said, when I said, well, what's the cost per watt? He goes, I don't know. And I go, well, what do you mean you don't know? If I ask the wind guy or the PV guy, he can tell me. He goes, well, the issue here is that they've got at least a 20 and probably a 30-year head start on us in terms of maturity, and ours is so dependent on commodity costs like steel and glass and so forth. Steel in particular, he said, which I found to be a remarkable response. Um, but anyway, there certainly are issues with respect to you like the fact that you can store the energy as heat because it's obviously less expensive to store energy as heat than it is as electricity. Having said that,
Well,
you're
that's
right.
what everyone says. Yes, I'm not so sure about that. But I think the cheapest way to store energy is pumped hydro. Uh, but then I think, as we'll see, it's also easy to store it chemically, even though there are losses. But
Right.
yes.
Okay. Well, why don't we move on then? You want to talk a little bit about wind because I have a guy approached me with all excited about this compressed air energy storage adjunct that he had on his wind farm that he was proposing, and talked about a whole bunch of technology to work out the kinks on this thing. You believe, I seem to recall from our conversations, that there are issues with respect to thermodynamics that make this thing a lot tougher than it appears.
Indeed. I think that there have been two significant demonstrations, one in Alabama and one in Germany, that have been there for several decades. And yes, it will work in some places, but efficiencies are typically in the range of 50% energy in to energy out, or maybe 40%. In that range, they can go up maybe to 55 or 60% with adiabatic advanced methods. But another severe limitation that's almost always ignored is those efficiencies actually are when the compressed air storage is used optimally, where the rate at which you are storing actually increases with the pressure of the cavern, and the rate at which you're removing, drawing energy from the reservoir also depends on the pressure. So that means you have very limited flexibility. You have to charge and discharge at a specific rate dependent on the pressure in the cavern to even approach those efficiencies. If you want higher or lower rates than dictated by that optimum, there's substantial additional loss in efficiency. And I think that as they look into these details, those who have advocated it, they realize these problems are not going to be solved. There's been a study of one project for, I think, about a decade in Iowa that has really gone nowhere. I think it's probably not going to materialize, but I know there will be a few projects funded over the next several years. The DOE will support that, but I don't think we'll see them being competitive. Pumped hydro, on the other hand, where the natural terrain permits lakes at two different levels, it's great and will be competitive, but there'll still be limits on how much can be stored, depending on the reservoir size.
Doc, you're breaking up a little bit. I don't know exactly why, but if you can just be as close to the microphone as possible.
Okay, try again. But yes, pumped hydro, I think, is the most competitive in areas where you have elevation differences to permit a lake at two lakes that had different levels.
Right.
You can pump between those two levels and store a lot of energy and recover it.
Yes. Well, you mentioned this thing about compressed air, that they're details. They sound like more than details to me. If it's really true that the power, in other words, the amount of energy per time that you can especially discharge, if that's truly limited, or you take a huge hit in efficiency, that sounds like a disaster for compressed air to me, simply because the whole point of this stuff is to be able to put it on the grid as on
in the compression, the temperature of the air is increased dramatically, and the cavern must handle that. If you have a large heat loss in the cavern that's not put back into the gas upon use in it, then there's additional loss there. So, yes, net efficiencies will typically, I think, be a lot lower than what the advocates are claiming for their ideal conditions.
Okay. Well, let's move through. So I think we have just one or two more slides before we get into your solution. A couple of people, there's some pretty heavy-duty people associated with this ammonia as fuel issue. They've got problems to solve. I'm not sure what about the technology? I know they got horrific public relations problems. The DOE doesn't consider ammonia a fuel. It considers it a toxic chemical. So, but anyway, what are some of the, just take us through these other three quickly, please.
Well, I think that's the biggest challenge. The attraction of ammonia is you can make it out of air and water. You don't need to pipe in CO2. Nitrogen is very abundant in the atmosphere. So Matt Simmons was a very strong advocate of using wind energy to make hydrogen and react that with nitrogen in the air to
Yes.
make ammonia.
Right, that's where I first came across it.
But it's, of course, not stable at atmospheric pressure and temperature, so it has to be stored in high pressure, and it's a caustic liquid, and it leaks, and it's noxious, hazardous. The public will not accept that as a fuel. Its energy density also is not nearly as high as hydrocarbons, so it wouldn't be as desirable from that perspective. There are much better options for liquid fuels, the ones that we've been using for more than a century. They're much less toxic and higher energy density. So the only thing going for ammonia, I think, is its process has been understood pretty well for a century, and you don't have to pipe in CO2 to make it as you would for synthesizing hydrocarbons.
Right, and the fact that it doesn't have carbon in it is probably attractive. In other words, people say, as long as we're burning hydrocarbons, we've got an issue. Now, I know that you don't necessarily agree with that, but I'm sure there are, people who that would be their first reaction to this.
You're absolutely right. Many people don't immediately understand that. They accept biofuels. They may not even know that biofuels have carbon in them. Those are the kind of people that will have difficulty understanding that wind fuels are
right.
Carbon neutral.
Okay. Well, why don't we go, here's a slide on your levelized cost of energy, if you want to just hit the highlights here.
I list the capital costs of several different sources. These numbers are from a little over a year ago, so they're not all current. Capital costs, capacity factor, that is what fraction of the time does the source normally operate, and O&M, operating maintenance costs, fuel lifetime, typically. Then the levelized cost of energy, dependent upon, as we see here, two different interest rates, 5% or 10%. And these numbers are staggering as you get toward the bottom of this table for enhanced geothermal systems. They've had very high capital cost and high operating costs. Compared to at the top of the table, I list wind and prime zones. Of course, it's more expensive in some other places, but is clearly quite competitive with clean coal and even conventional coal as the price of coal goes up, even when the coal plants are already paid for. Wind will often compete. There in the middle, or sort of closer to the bottom, CSP and PV. Now, the CSP costs are still as valid as they were a year ago. The PV costs have come down, but what we often hear for PV costs, manufacturing costs of the cells, is only a small fraction of total cost. You have to look at the total installed cost, and when you do, you see it has a long ways to go before it will be competitive with coal in most places.
Okay, well, now let's go. I'm reminded of this conversation, by the way, to mention Matt Simmons. I was probably an hour and 20 minutes into this talk with him, and I said, well, Matt, this sounds pretty gloom and doom. Am I supposed to just, jump off a bridge? In other words, is there a solution on this thing? And that's when he got into his thing having to do with offshore wind and ammonia. You want to take us in the direction of synthetic fuels, and why don't you just make this presentation?
Well, yes, there have been a number of proposals for making synthetic fuels from clean energy, whether that be wind or another source. Nuclear has usually been proposed, actually, and carbon dioxide. But we've actually probably seen more proposals for making methanol from CO2 and hydrogen. But we think it makes more sense to make the high-value fuels that'll make it easier to economically support the process. But yes, the DOE has supported some synthetic fuels projects for the last 3 decades, at least, and they haven't been successful in the U.S. Coal to liquids, while there have been some small demonstrations, but there are reasons that I think we understand quite well why their costs just have soared, and it has something to do with their belief that the reactor needs to be a three-phase reactor. We think two-phase is much better. Also, in the separations process, they are looking at the kind of processes that are used in petrochemical plants at very large scale. They don't work well at the kind of scale where we need to start if we're using renewable energy. We really can't start at 100,000 barrels per day. We can't easily start even at 1,000 barrels or 100 barrels per day. We have to think in terms of a process that can be competitive in that range with 100 to a few thousand barrels per day. That requires a number of changes compared to the approaches that have been used in South Africa, for example, from coal, in their coal to liquids, where they're making fuels at the rate of 50,000 to a few 100,000 barrels per day. Their processes work well at that scale when the coal is cheap and when they're not concerned about CO2 emissions. We're concerned about CO2 emissions, and we've put the effort needed into figuring out how to make design processes that will work at the scale that's appropriate for renewables getting started, a renewable process getting off the ground, distributed generation at a rate that one can imagine being supported by locally available off-peak wind energy.
Okay.
So,
that's what I'd like you to get to, if you don't mind. So we're talking. So the energy is off-peak wind, and your belief is that there's a lot of that, but there's controversy about this. In other words, what's the deal with off-peak wind as we sit here today in June 2011?
Well, the wind industry didn't like to admit that that was a problem until they were forced to. Within the last year, it's become such a problem. They try to get good prices in their power purchase agreements, $50 a megawatt hour. The fact is that there's more wind energy available, produced then in the middle of the night than what the local market can use, and so utilities are forced to sell excess energy in real time at prices near zero and actually sometimes even negative. And the amount that they have been selling at near zero prices or curtailing has just dramatically increased steadily for the last 4 or 5 years. For the last 3 years, the amount of wind energy curtailed, that is where they turn the blades so they're not generating energy, has tripled annually in the United States. And
okay, let me just see if I can understand this, because so this is due to a glut of wind without storage, essentially.
Right, in areas where there's not transmission capacity to get that energy to the markets, the distant markets, they have nothing to do with it but to stop generating.
Okay, now for how long? If I were an investor on this thing, I might say, well, this this looks like a good solution if you could scale this thing this week. Um, and it looks like a good solution that's going to have a window of opportunity, but it's a little hard to estimate how long that window is going to stay open, because as soon as we've built out our grid such that we can, take wind out of, the plains, let's say, and send it to the population centers on either coast, and certainly as soon as we can store it with some other solution. um, what you're saying is that this really is a solution that's going to be around for some time.
Yes, we haven't gotten much into that. Maybe the next slide might take us more into that solution. I can come back to that question maybe about how much energy we'll see available in off-peak hours at low prices.
Okay. Yeah, let's go through this. So there are a couple of things on technology here. And again, recognize that you're speaking to a non-technology audience generally. I mean, we're more business people than we are technologists, so I'm going to ask you to scale back your presentation so that people like me can understand it.
Well, Fischer-Tropsch synthesis has been used extensively in South Africa. They were embargoed because of their apartheid regime, and they had no choice but to make their own fuels, and had lots of coal. And so they were under pressure. They figured out how to do it. They did it competitively. So it can be done from coal. The problem is the way that process works. They start by partial oxidation, is what it's called, of the coal to get carbon monoxide and hydrogen, and that's then reformed into liquid fuels. Problem is, enormous amount of CO2 is released in the process, and in fact, Sasol is the world's largest point source emitter of CO2. That gives you some clue as to how much CO2 is released, and that's just supplying a fraction of the oil needs there in South Africa. So we can't go in that direction, making our fuels from coal or methane if we are concerned about the climate.
Right.
There are other issues that make it very expensive. Cleaning up the syngas, especially from coal, accounts for 50% of the cost of the plant. So it's not cheap if done at small scale, especially. We need something better. But we can build on some of that chemistry, some of the things they've learned, and make it work because of this opportunity we were just talking about. Here we see the price over the last several years of peak energy, average, off-peak energy, and cheapest in the MISO hub, which covers most of a six-state region, Minnesota and surrounding areas. And the price of energy has dropped dramatically with the growth of wind, and then when the price got too low for wind to be attractive, growth of wind stopped, plateaued. That's that blue line flattening out, and until there were again reasons to build, and then the price dropped again. And so they produce a lot of energy there at low cost. The amount available is increasing, and we're going to use that in the process then that we've been working on for making fuels from CO2.
Okay. So what you're saying is that this whole issue of synthetic fuels is a reality. You take a lot of energy that is otherwise essentially wasted, and you reform the carbon from CO2 and the hydrogen from water, and there is obviously there are losses, but they're acceptable, and thus you get to this kind of summary. Is that correct?
Right. So there are what are called renewable portfolio standards, or the new popular term, more popular term, I guess, is renewable energy standards, that are requiring most states to add to their renewable energy, renewable electricity capacity at a very rapid rate over the next 10 years. And the only way they can do that economically is with wind in most places. There are a few places where they will add some solar, but mostly they'll meet their RPS standards by adding wind. So
Right.
that will ensure increasing availability of low-cost wind energy, and with that, we'll be able to make the fuels that we need in our cars, and they'll be carbon neutral.
Well, this is interesting. I came across a guy yesterday who raises money in this market, who's concerned that the utilities really don't want to do this. And it's true that they're being forced in some circumstances, but there are other places where you can't get they have power purchase agreements that are kind of being overturned. They go to the Public Utilities Commission and say, look, we signed this, but now we don't want to do it. But your viewpoint is, even in the absence of a federal renewable portfolio standard, there's enough teeth in the state RPSs that we are, in fact, going in that direction?
Well, indeed, and yes, you did raise a very alarming point there. The Bonneville Power Association, I guess, has reneged on contracts recently, and we'll probably see more of that as they decide that they just simply have to abandon their contracts to avoid losing money. But there's an uproar caused by that, and then we'll probably see few cases like that. So there will be continually more wind driven by these RPSs, and that will mean there'll be a lot of curtailed energy that can be utilized.
Right. Very good. Well, we're coming up on a diagram of this process that I'd like you to walk us through. Before we get to that, let me just remind listeners that if you want to write in on the sidebar on your left, if you want to write in questions, I'll certainly present them to Dr. Doty at the appropriate time. Let's go back, and here's this slide. I hope this is visible. That's legible, isn't it?
Yes. There we present the concept briefly, simplified. We start with off-peak electrical energy to get the hydrogen we need by electrolyzing water. Some of that hydrogen will be stored because we'll want these chemical processes to go fairly steadily around the clock. The hydrogen, some of that then goes with carbon dioxide into reverse water gas shift process that reduces this carbon dioxide to carbon monoxide. Carbon monoxide and hydrogen, then, we can work with. We can make the hydrocarbons we want in using the same types of catalysts that have been used for 3 decades in Fischer-Tropsch synthesis. That's in the FTS reactor. It needs more hydrogen than just what is required for the RWGS process. So about a third of the hydrogen, in fact, was used in the RWGS process, and the remaining with carbon monoxide goes into the FTS reactor. Out of that come hydrocarbons, full range. One of the drawbacks of the FTS process is that it's not highly selected. That is, it doesn't produce a single hydrocarbon or a small number of hydrocarbons. It produces a full range of alkanes and alkenes, from light to heavy.
Which are the essence of our fuels, but what you're saying is that alkanes and alkenes need to be separated out. You can't fill up your tank with apples and oranges. Right.
What comes out is sort of like ultra-clean crude oil. Crude oil has the full range of hydrocarbons from a little bit of propane even, but pentanes up through light waxes. And that has to be processed to get high-octane gasoline or diesel that flows well in cold weather, likewise jet fuel with proper burn characteristics. It does require a large number of steps, separations, and other chemical processes known as alkylation or isomerization. These things are well understood, and they're not expensive and don't require a lot of energy. The advantage, what's coming out here of the FTS reactor, doesn't have the noxious contaminants that the poisons, as they're called, that so shorten the life of the catalyst that you have in conventional crude oil. So it's easier to do the separations. It's just the pure hydrocarbons, but then you separate them into the weight ranges that are needed for the different fuels and do the further processing to get the characteristics required to meet the specifications for motor-grade fuels. But then what comes out is just like what we get from petroleum, except even lower levels of sulfur and other contaminants.
Okay. So your proposition then, well, let me ask you this. There are other people working on synthetic fuels. In a sentence or two, what makes this unique?
I'm not aware of anyone else that's trying to make fuels like this from carbon dioxide. They're starting from, generally now, from methane. Natural gas is perceived to be abundant, and it will be easier. You won't have to have hydrogen. You can just reform the methane. And so gas to liquids, yes, will increase. There'll be more of that. And some are still working on coal to liquids, although that's not being supported much. The other synthetic fuels approaches that I'm aware of, they're trying to make methanol because the process is simpler. Because, yes, you really do want to have some carbon monoxide to go into the reactor to produce the methanol, and some think you might be able to get catalysts that will work well without carbon monoxide, just carbon dioxide and hydrogen. Coming out of the methanol reactor is really just methanol. And so you don't have a complicated separations process following it. But what you have is a low-value product. And that's why we think it makes sense instead to focus on getting this process right so the products coming out will command the prices necessary to make this economically viable.
Yes. Well, it does strike me that this is a common denominator of exciting business plans. In other words, I've got a guy, I may have told you about my guy also in your neck of the woods, South Carolina, who has a waste tire, a pyrolysis process that actually creates diesel. So in other words, it's not an intermediate fuel, and the fact that this technology is good enough, it's actually not proven in the United States, but it's Taiwanese, they've got several plants in Asia. And not that it matters what continent it's working on, of course, but the fact that it's producing, a fungible diesel fuel is extremely exciting to investors, and it looks like you're onto the same type of thing. In other words, instead of creating a low-grade fuel that has questionable value, you're, shooting for the moon, so to speak.
Yes, and the problem with making fuels from tires is there's a severely limited supply. There are other problems, too. I think lifetime of the catalyst. That is a challenge with all pyrolysis processes, pyrolysis of biomass or any kind of waste. Yes, that will provide a small source of fuels, but the feedstock's limited, and I think maintenance of the catalyst is also a challenge.
Okay, well, it'll be interesting to see where that goes. Here's a question. Actually, coincidentally, this is Dr. Herbert Zeman. Dr. Zeman, I hope I'm pronouncing your name correctly. And this is one of the questions that I asked Dr. Doty when we first met. What about the charging of EV batteries? In other words, we could put 90 million, I guess the issue is that we haven't got 90 million EVs on the road, but we could put, according to reports I read anyway, many tens of millions of EVs on the road this afternoon and not create a single additional coal-fired power plant or any other simply because of off-peak energy. So Dr. Zeman asks, isn't the charging of EV batteries a good use of off-peak cheap energy?
Well, yes, if the vehicles were there, it would. It does make sense that more wind would be used for that. There'd be less curtailment if there was the steady market there from electric vehicles if they charged in the middle of the night in areas where excess wind was available. But of course, the excess wind is mostly far from population centers, and there's not adequate transmission capacity. So, and the time required to put up a new transmission line, The project times are typically 7 years or even longer, and then you're talking about perhaps small addition to the capacity. So it's just not going to happen quickly. There are a lot of people doing what they can to get there, and we're seeing some slow progress,
Yes.
but it'll be limited.
Right. What I see also on this thing is a legal as well as a technologic issue. I was disappointed to see a Supreme Court decision in the last 12 months, I don't remember exactly when, that kind of struck down a lot of what we take for granted in terms of eminent domain. In other words, we believe that simply because we have a way of moving cars across the United States, i.e. the highway system, and natural gas, that we could do the same thing with a few lousy electrons. But the issue, even if we have great high voltage DC technology, the issue of using eminent domain to move this around to the population centers sounds like a troublesome endeavor at this point, which really is a disappointment to the people who go, look, we can move train cars around. Can't we? Are you telling me we can't move electricity? And the answer seems to be yes.
Indeed, that was a surprising ruling, but it tells us it's going to be a long time before we have the transmission capacity that we need to support cars in New York City from wind farms in Kansas.
Yes, exactly right. Well, I think, again, taking the viewpoint of a potential investor, I think one of the things that attracts me to your presentation is that it's not so overly ambitious that investors go, this guy may be a scientist, but he's clearly not a businessman. So do you want to take it? Here's a slide that talks to what I think is the kind of brute reality of the thing. In other words, what are you trying to do, and at what level, and in what time frame?
We are working on R&D issues, indeed, simulating sub-components, sub-processes. We are putting together some apparatus so that we can do experiments to evaluate catalysts that maybe haven't been adequately evaluated at the conditions that are needed to get the best economics. There's data on a number of catalysts that will work in the reverse water gas shift process, but it's limited data, and there are questions. So we need to evaluate other options under the conditions that are likely to work best. We need to make prototypes, small scale. This is going to require resources. We have limited resources. We're working at the rate that we can support. And we're always thinking ahead, the next size. Maybe we'll start with a 200 kilowatt plant and then go to a 2 megawatt, but we have to be thinking about how it's going to work at the 100 megawatt scale. And the processes that then we're going to use in these small demonstrations may not be the cheapest or easiest way to do a quick demonstration, but we know they'll allow us to better support our projections to a larger scale. So we're working on that, looking for investors that appreciate the opportunity here, that we're talking about a process that really can scale to the trillion-dollar level. That's way beyond the potential for any of the biofuels. And some investors do understand that, but they're slow yet to move, I think, until they see more data. We think we'll have a lot of good data by the end of this calendar year, and even by early fall, that will make it easier for people to understand the potential without going through the details of all the physics and chemical engineering, and the simulations are difficult to follow, and it's difficult to commit the resources to do those detailed evaluations. But if they can just see fuel coming out, clean fuels of several different types, then that convinces them that we know what we're doing.
Yes, I can see that happening. Good for you. If I, here again, I just want to remind people that they can write in questions. If I'm doing the math correctly, if you have 200 kilowatts and you run it at night, run it all night, let's just say 10 hours, is 2 megawatts divided by, I guess it's like 30 or 35 kilowatt hours per gallon. You're talking about a barrel of fuel, plus or minus?
Right. From our first demonstration, we expect that scale will be in the 30 to 33% efficiency range. So if we run 200 kilowatts continuously, yes, we would produce a barrel a day, roughly. And as we go to larger sizes, the efficiency will go up. But yeah, those are the rough numbers.
Okay. I think I'm going to go out on a limb and try to read what Jean-Gerhard Hemming has written here. Hold on to your hat on this. Reverse water gas shift for reducing CO2 to carbon monoxide means that 1/3 of the hydrogen needs will produce water. And he goes CO2 plus 3H2 goes to methanol and water. What about, he asks, carbon dioxide plus 2H2 goes to methanol and a half O2? Could it work, he asks?
Well,
here I'm asking you this where I swore I was going to keep this keep the chemistry and physics out of this thing, but it does. I know this guy actually is extremely highly, embedded into the synthetic fuels thing.
Indeed. With the right catalyst, you can get good yield. The problem is you're producing methanol, which the market for that is about half the price of gasoline per unit energy.
Right. That is CH3OH, right? CH3OH right. Is methanol, right?
Right.
Okay. Okay, well, very good. Thank you for the question. We have another question about fuel cells. I think this is I'll just read this question. What's the cost of using fuel cells to get peak electricity from the hydrogen and oxygen gases produced in the electrolyzer? And the answer is we're not doing that. We're using the hydrogen in a different way. Is that correct?
But I think that that's a good question, and I think that we will see that at these wind fuels plants. When you have hydrogen available and you've stored it there to keep the process going steadily, and fuel cells continually become more competitive, especially for stationary applications where you don't have the hydrogen storage issue or it's already taken care of, then certainly it makes sense to have hydrogen fuel cells there to provide some additional peaking capacity. I think that will be more competitive than batteries when you have the hydrogen in place.
Okay. Interesting stuff. Well, this has been a terrific session. Dr. Doty, thanks very much for being on the show, and we will definitely look forward to hearing where this goes. I would urge everyone listening to write in through 2 Green Energy. If you just hit the contact button and send an email if you have further questions for Dr. Doty or me. Though Lord knows I'm not very well equipped to handle the technology issue on this thing, but if you're interested in speaking with Dr. Doty about a business or a technologic issue on this thing, please let me know. Just write in through the contact button. And here's one last question. How many barrels of fuel will you produce from an acre-foot of water? I guess the issue is we get plenty of water. He goes on, in order to replace a significant number of barrels.
That's an enormous amount of water. Let me answer it a little bit differently. It'll typically take about 1.5 gallons of water to produce a gallon of fuel.
Oh my. So water's not the issue.
Right.
Well, a good question, though, and I don't think we've talked about this thing, is where does the carbon dioxide come from, considering it's only, whatever it is, a couple % of the Earth's atmosphere, unlike nitrogen. I'm sure the ammonia people would point that out. So you're proposing to get this where?
Right. There's an expanding CO2 pipeline network. It's used for enhanced oil recovery. We will need to locate generally close to a good CO2 source. It may be near a CO2 pipeline, or it may be near a cement factory or a biofuels plant that's releasing a lot of CO2. There are a lot of sources. Those would be some very clean sources, also ammonia plants release a lot of CO2 that's very clean. But the pipeline network for distribution of CO2 for enhanced oil recovery is expanding, will continue to expand rapidly. I don't think it'll usually be too difficult to get close, locate close enough. You could always transmit the power a few hundred miles if necessary, although there would be losses, and likewise there are losses with piping CO2 distances. So it's a compromise in, with respect to your inputs where you would situate the plants.
Yes, I would think that would be an important decision to make properly.
Indeed, but it's not probably the biggest factor with respect to economics, but one that will have to go in to the mix.
Okay, well, very good. Dr. Doty, again, thanks so much for being on the show. Please write in through the contact button at 2greenenergy.com to continue the discussion. I will, by the way, have this webinar archived and up on the site in the next couple of days as soon as I can get some of my tech people to take care of it. Thanks so much for your time, everyone. Talk to you again next month.
Thank you, Craig.
All right, so long now.